Welcome to Dunwoody College of Technology. This is Mechanical Engineering 3250 heat transfer. We're doing problem 1220 from Bergman today. So in this problem we have a few things going on. We're told what the solar radiation heat flux is on the surface of the Earth's atmosphere. So we know that that is about 1400 watts per meter squared. We also happen to know the diameters of the Earth and the Sun. So the Sun is considerably larger than the Earth. No surprise there, but we get those values. And we know the distance between these two. And so we're asked, what is the emissive power of the Sun? And then once we have that, we can find what the Sun's surface temperature is. So this is E sub Sun, this is T sub Sun. And then the wavelength, where the emissive power is a maximum, that's going to be lambda max. And then if the Earth is assumed to be a black body or black surface, and the only source of energy for the Earth is the Sun, find the Earth's surface temperature. This would be T Earth using an energy balance. So we know these various pieces. We know that's we know our radiation received at the surface of the Earth. So I'll jump to a schematic. So we have the Sun here. Happy Sun. So ds, diameter of the Sun, is 1.39 times 10 to the 9 meters. Then some distance away, smaller, is d Earth, which is 1.27 times 10 to the 7th meters. And this distance, I'm going to call it radius Sun to Earth, is 1.5 times 10 to the 11th meters. So what we're trying to find is how much of this radiation is going to actually hit the Earth here. So we'll make some assumptions. One, we'll assume both bodies are black. We haven't looked at real emitters or absorbers yet. Second, we'll say that we don't all solar radiation toward Earth reaches Earth. Reaches the atmosphere. And third, we'll say the atmosphere doesn't interfere with the radiation. Alright, so with that, we'll jump into some analysis. So the first bit is to find the ES, the emissive power of the Sun. So we're going to have, basically, the way we'll look at this is say, we'll have the Sun, and then farther out from that we'll have this other surface, and we're looking at how much of this radiation actually goes through where this is the diameter of the Earth. So it makes sense. We're doing two concentric circles. Spheres. I'm going to do this bit from here. So the emission from the Sun is that emissive power times pi, which is a solid angle here, ds squared, and that's going to be what we receive over at 4 pi times the radius from the Sun to the Earth, this bit, minus dE over 2 squared times that heat flux we'd measured. Right, so this is what we're receiving at Earth, this is what we're giving off from that, and these 4 pi pieces here are the essentially the percentage of that that reaches the Earth. So ES 4 pi RSE minus DE over 2 squared QS prime over pi DS squared. So that goes away. Filling values in. 4 times 1.5 times 10 to the 11, not negative 11, excuse me, 11 minus, what was that, 1.27 times 10 to the 7 over 2, is that right? Go back up, yep, 1.27 times 10 to the 7 over 2 squared times 1368 all over, so 1.39 times 10 to the 9th, 1.39 times 10 to the 9th squared. So what do we find? When we plug in those numbers, we find that the emissive power of the sun, or the total emissive power, there's no lambda under this, is 63,718,014.6 watts per meter squared, or 63.7 megawatts per meter squared. It's a lot of power. So that was part 1. Part 2, the book has it A, B, C, D. Part 2, we're looking for TS, temperature of the sun. If we have the emissive power of the sun over here, we know that from Stefan Boltzmann is sigma TS to the 4th for a black body. So it's as simple as TS is ES over sigma to the 1/4. So plugging some values in, what we found up before, 63,718,014.6 over 5.67 times 10 to the negative 8 to the 1/4. Plug that in a calculator, and we find that our temperature is about 5,790 Kelvin. That's pretty good. Matches up with other measurements that are a little more accurate than our rough model here. Part C, or part 3 as I'm calling it, we're looking for lambda max for the sun. So we're going to use Wien's law, and that was that lambda max times T, some constant C3. So for solving that, lambda max C3 over T S for the sun, and C3 was 2898 micrometer Kelvin. We're going to divide by that 5790 Kelvin, so we'll be left with micrometers. Lambda max works out to be 0.5005 micrometers. So about half a micrometer. Last, T Earth. So we're going to have to do some energy balance. I hinted at that earlier. On Earth, what do we have? So we have what we have receiving, what we have going out. Let's do that. So we have the emissive power of the Earth times that area. It's going to be equal to the heat flux that we're receiving at the surface of the Earth times pi dE squared over 4. So we're looking for EE here at this point, and we're going to use that to find TE. So EE, QS double prime pi dE squared over 4, kept that there, over pi dE squared. So these guys cancel each other out. Emissive power of the Earth is QS prime over 4, 1368 over, I'll leave that there for the time being. So we'll fill in the numbers a little later. And then this is also equal by Stefan Boltzmann to sigma TE to the fourth. TE is going to be EE over sigma to the 1/4. So TE is going to be this guy, 1368, filling that in now, over 4 times 5.67 into the -8 to the 1/4. TE works out to be 278.7 Kelvin. Or we can call that TE 279 Kelvin. So it seems a little cold, but we're also assumed earlier that the atmosphere doesn't interfere. In actuality, it allows the low wavelength, high frequency radiation in and helps trap some of the lower frequency, longer wavelength radiation in. So just out of curiosity, I'm going to check this out for lambda max for the Earth. It's going to be that 2898 micrometer Kelvin over 278.7 Kelvin. Lambda max for the Earth. What is that value? That works out to be just about 10.4 micrometers. So about 20 times the wavelength of the solar radiation incident on the Earth is the radiation leaving the Earth. And so that gets more trapped in the atmosphere, and we see our temperature run up to closer to about 300 or so Kelvin as a global average. So I hope that was helpful. Kind of big picture, where do we come from, where do we go? We're looking for these emissive powers, knowing a heat flux at a given point. We made this model that we have solar radiation going all these directions. We're looking for the little bit that hit here. What percentage of that was the area on the sun? So we found the emissive power using that relationship. Then using that emissive power, we can calculate the black body temperature of the sun, and that worked out to be about 5800 Kelvin. Using that value, we can find the wavelength with the max power of at the sun. That worked out to about half a micrometer. And then last, using energy balance on the Earth, we could find the average temperature of the Earth, and that's a little low, but for reasons of our atmosphere being ignored in this, we found a lower value than we actually have. We found about 280 Kelvin as a result. So I hope that was helpful. If you have any questions, feel free to hit me up on Teams if you're a Dunwoody student, or you can reply in the comments here. Thanks.